In this video, we're going to go over what we did in the previous video, the prospect processor. Now I know what you're thinking, man, Cybernaut, you must really hate this class. I mean, I kind of do, but I'm not going to go over the issues I had with this again. This is going to be brief. I want to go over the 16 dependencies again. Not so much as to why I don't like the 16 dependencies, but focusing on what they are. These 16 dependencies, they are explicit interfaces. Again, recapping from the previous video, explicit interfaces are a means for an entity to provide external functionality to other entities to utilize and call. The problem, though, with explicit interfaces is that they do not provide the implementation as to how to complete that external functionality. That's actually within a concrete type. So the question then comes, how does the concrete type actually get utilized in a structure like this? Okay, I'm now done with the prospect processor. I promise. Let's just push that to the side. Let me pull in a new concept called a canvas. Now this canvas, as you can see, takes in a dependency of an I shape. And that I shape is, like you guessed it, a rectangle, a circle, whatever you want it to be. And as you can see in the canvas, there's a method called draw right here. And that draw method will actually draw the shape that is passed into it. The intention of this class is just to draw a shape on a canvas. The question then arises again as to which shape is utilized in this canvas class for the I shape. The one way to do this is just to implement what shape to actually use in the constructor of this class. For this example, I'll use a rectangle and the canvas will draw a rectangle. Cool. The issue with this approach is that the canvas class, which is pretty general in its use of just drawing any shape it wants to, now has to only draw rectangles. If I wanted to, say, use a circle, I would have to update the canvas class to utilize the new circle that I create in the constructor. The term for this is tightly coupling. The canvas class is tightly coupled to the rectangle implementation. How can I go about making it so that the canvas class doesn't have this tight coupling to the rectangle's concrete class? One solution I can do is to create, say, a module class that will create a new canvas class with the rectangle injected into it. Therefore, the canvas class doesn't need to rely on the specific rectangle implementation. It can just rely on the explicit interface of the I shape and draw whatever I shape the module class passes into it in the future changes it may have. Instead of relying on the canvas class to utilize the rectangle within its implementation, we invert the control of what dependency the canvas class has within the module class. This is a form of inversion of control. Inversion of control is a general concept in software development where control is granted to some other part of the application to provide dependencies or callback or reactive functionality for low-level concepts to get into general type concepts. So in this case, the canvas class, which is a general concept of drawing shapes, does not need to rely on the specific low-level concept of a rectangle. We inverted the control to the module class. The type of inversion of control I implemented here is known as dependency injection. The dependency injection is just a way to provide the dependencies to a class within the constructor or getters and setters. In this example, I provided the rectangle class in the constructor to the canvas class. The canvas class now just relies on the I shape, but the module class now relies on the rectangle class to pass into the canvas. The specific implementation I used here for dependency injection is known as Pure DI, Pure Dependency Injection, or the other name I prefer, Poor Man's Dependency Injection, because I'm frugal. Current trends in software development don't appreciate the nuances of pure dependency injection as I do. Current trends are focusing more on something called an IoC container, Inversion of Control Container, or probably more aptly named a dependency injection container. Now, this IoC container is a single location typically in your application that maps all the dependencies, interfaces, abstract classes, those type of things to a concrete class. And then on construction time of runtime, of the application, these dependencies, these mappings, are set up to create the object graph behind the scenes. In the next section, I'm going to implement a rudimentary example of an inversion of control container. I feel like it'll be helpful for all of us to get on the same page and kind of understand what's happening underneath this type of design. I also feel like, from my experience, people don't truly understand what is actually happening under the scenes and how this structure actually works. I'll preface this by saying sorry about the amount of time this will take to set up, but I think it's important. So I'm trying to create an object graph that is 3 levels deep. They're going to be interfaces for the start. iRoot class is the top level. I first level A and I first level B are actually the second level, probably not the best name. And then I second level A and I second level B are the third levels. So root class takes in I first level A and I first level B as dependencies. And then first level A will take in I second level A and I second level B as dependencies. And first level B is just a duplicate of that with I second level A and I second level B as dependencies as well. So second level A and second level B are just parameterless constructors, easy enough. So as you can see, I'm writing out what the root class object graph looks like. This is using the Pure Dependency Injection method. I'm just doing this right now just to make sure there's no errors or build issues as I compile and try to run it. And let's see what happens. Yep. So this is working. It prints out the obligatory hello world, so all's good. So one of the issues that I'm trying to address right now is that nothing actually prints out for the object graph. So I'm creating this interface iSerializable object graph and applying it to all the interfaces, which now require all the implementations of those interfaces to do that. All that I'm doing is just creating kind of like a formatted object graph of root classes at the top, and then there's a tab for each subsequent level going in. So first level A is a two tabs in, and second level A and second level B are 3 tabs in. So let's see if I can actually print out the object graph. Yep, prints it out, root class at the top, and then 1 tab in is first level A, and then 2 in is second level A and second level B. Now what I'm doing right now is adding a referential thing. I want to ensure that the objects that I'm creating are different. So for example, the first level A and first level B both have second level A and second level B. I want to make sure those instances are different. I'm adding a referential entity abstract class that has the ability to get a GUID. A GUID is a unique identifier to show that these are different classes, instances of the class that's created. And I'm just appending that to the current structure we have to ensure that the referential integrity is as expected. All these references should be different. So added it, I ran that, and that's good. I get the GUID showing there again. GUID is a global unique identifier to ensure that all these instances are different. So it's printing out appropriately. Actually, no, I think I may have messed up something. First level B seems to have the same GUID. I think I may have printed second level A twice. So yeah, that's what I did. Let me print out second level B. It's not in the implementation. I just printed out the wrong thing. So yep, now they're unique. But oh, I have the same issue with first level A. First level A, I copied that for first level B, so that I have the same issue. I copied the same issue. So all right, now looking at the end result, yeah, all these GUIDs are unique across first level A and first level B. No GUIDs are duplicated. So all this looks good, and yep, awesome. Again, sorry about the amount of time it took that thing to be set up. I think it's important that all of us are on the same page, even kind of this setup mentality. It takes a while, but I think it's going to be very beneficial going forward as to how we got where we are, and we can reference it later to see what the issues are. Now, when we got done, you could see that I did the Pure Dependency Injection like I demonstrated early on in the video with the shape idea, shape concept. Now the question is, how do you do this with Inversion of Control Container or Dependency Injection Container? So let's continue on and let's get to it. Okay, let's start building our own IoC container. So the intention with this is I want to have something that has the ability to bind a interface to a concrete type. So for the example, iRoot class should create an instance of root class behind the scenes. So I want to do something kind of like bind iRoot class. This is the from something to a root class, the concrete type. I'll be using generics for this. This is what's in these less than and greater than signs. And again, this is the iRoot class is the from. So I want to get an instance of an iRoot class, and the actual result is root class, but the actual thing that's utilizing whatever this is does not know that it's going to be a root class. It just knows that it is a iRoot class, and it actually created an instance behind the scenes. So for this first kind of pass through, we just need to create some sort of mapping structure that takes in kind of like a key, and then what's the value that it should return. So let's go into our new class IoC container and create the definition of the class IoC container. And for this, I was mentioning like keys and values. There's a concept in C# called dictionary. It's pretty much what you think it is. It's an ability to look up a something. In this case, we're going to be looking up types, but it's the ability to look up a type, and the resultant value is another type. So for this, it's going to be the key type is an iRoot class, and the resultant value type that's returned from looking up that key type is a root class. So we'll call this thing mappings. Let's make this private. The only thing I should know about these mappings are the IoC container. Let's create a constructor, and we'll just set the mappings to a new instance of a dictionary of type. So let's create the binding method. The void bind. So again, this is just taking some type from, so an iRoot class, and I want to map it to a root class. So passing in iRoot class and getting out a root class, but treating it still the result as an iRoot class. But behind the scenes at runtime, the actual instance is root class. So we'll add some constraints to this. The from has to be an instance type. Class is probably not an ideal name. This class is different from this class. This can be like an interface, can be an abstract class, can be anything. It's the ability for like instance types, which interfaces will, if you have something that implements it, will be an instance type. So the assumption is that interfaces are going to be instance types. Let's say fall into this class constraint. So this is just a constraint on the generic type again. So from is instance type, that can be an instance type, and to is also going to be an instance type as well. Ideally, it's going to be a concrete type that can be created. And another constraint that it should have is that it is going to be a of that from type. So root class, for example, is an instance type, but it also implements the iRoot class. So this is just saying that I can create this thing because it is a form of this from representation. So something like iRoot class to a second level B wouldn't work because second level B does not implement the iRoot class. So that's what this second constraint is doing for this to parameter, this new generic argument. So let's just create the implementation for this. It's not going to be too difficult. Just do my IntelliSense Smart there, mappings, add a new lookup, the type of from, iRoot class for this example, and then the type of to root class for this example. So this will create all the mappings. So let's go in here. This should actually work. So let's create a var container equals new IoC container, and we can remove this and just do container dot bind. Cool, so that works. So let's do the next one. So iRoot class does root class, and if we look at that, root class has I first level A. So I first level A needs to be represented as a first level A. That's the map to a first level A. So we'll just do that for all of them. So when we see I first level A in the object hierarchy creation, this dependency injection container will create a first level A. Oh, I forgot the A right here. Let's copy this. B, I first level B goes to the instance concrete type first level B, and then there's a I second level A that will go to the concrete second level A, and last is I second level B, and this is second level B. So I think the bindings are all set up appropriately. I'm not seeing any errors. This looks to be fine. Oh yeah, just to show kind of like that constraint I was doing. So let's add like a container dot bind I root class to a, let's say, first level A. It should probably, has a red squiggly because first level A does not implement the I root class. So this will not compile, which is what we want. That's why we added the constraint. So next, we have the bindings. Now we just need to create an instance of whatever type we want. So for this, let's should probably be something like getObject. And I'm not dealing with the concrete types, I'm dealing with the interfaces. So when I call this, behind the scenes, it should create this representation right here, this object graph right here should create a new root class with these dependencies, first level A, first level B, and first level A with these dependencies, second level A, second level B. So this should result in the exact same thing that's happening up here when I call this right here. The only difference is the representation here will be of type iRoot class as a result. This right here is treated as a root class, which is kind of one of the drawbacks as to how I set this up right here, but not too big of an issue. So let's create that getObject method. So public t getObject. So I'm saying t using the generic again. This will allow me to cast whatever type, strongly type I'm passing into this generic, to cast it as that type as the return. So let's put our constraint on this again, where t is class, because it should be the same thing right here. This from is going to be this t right here. And awesome. So first what we want to do is ensure that this t that we want to create is represented in the mappings. So to do that, let's just see if it's there. So if mappings dot, so tell sense pick that up. I don't want to know that it's in there. I want to know that if it's not in there, I want to flip this for the kind of like benefit of just bailing out early. So I'm going to throw an exception to say that if I'm passing a generic type that does not have a corresponding key, there's no mapping representation of that. So if I'm using like I3rd level A in here, assuming I have that interface, I didn't have a binding setup for that. So when it goes in here, there's no binding setups, hence there's no mapping. So hence it won't find this in the mappings, and it will throw this exception because there's no mapping found. So no mapping found for type and type of t dot name. So the generic is just the strongly typed like representation, but it's not the actual type itself. So I have to add this type of right here. This will specify to treat this generic type as the type strongly typed representation that's I'm using throughout this code segment. So that's what that type of t is doing. It's transitioning the generic to an actual type. So cool. So let's give a good name to what we're trying to create. So for this example, we want to take in this t, and that's the key, and we want to create the concrete type. So this is the to type. So iRoot class is right here, and the to type is going to be root class. So I want to create an instance of the root class when iRoot class is passed in. So let's just look up in the mappings, get type of t. So look up the key, iRoot class, return the value, root class. That's what that's doing. So now where we're at is we have this type right here, we have this root class, and we need to create it. So to create it, we need to call this constructor. Problem is this constructor has two parameters itself, and for this constructor to be called, these instances have to be created as well. Right now I haven't created them, so this is where kind of like recursion is going to be introduced. Not at the moment, but as I develop it, you'll see it. But in essence, I need to get this constructor, and I need to create objects, create the parameters for these as well. I first level A, first level B for this first iteration. So going back to here, I need to get that first constructor. So var constructor equals type dot get constructors, and I'm going to add single, as there should only be one public constructor for these mappings. I can show why at the end, because I don't have a working state right now, but the main reason for that is when you're running the application trying to create these dependencies, if you have a binding that says iRoot class goes to root class, and you have two constructors, or more than one constructor, it doesn't know which constructor to utilize to actually create the instance of the root class. So that's why typically you might run into when using your own dependency injection container, that is you have a concrete class that you're trying to map to, and it has more than one constructor, the original mappings will fail, and talk about how I can't do this because there's multiple constructors. It's the same principle here. Again, I can show you at the end an example of this, but that's why I'm adding it right here. So go back to root class. I have this constructor. I need to get these parameters. So how do I get those parameters? I will first create a array of constructor parameters. So constructor, so new object of constructor dot get parameters dot length. So this is going to create an array of all the constructor parameters that exist for this constructor, in this case the root class. So the end result is going to have two elements in the array. The first one will be an instance, an actually created instance of a I first level A, and the second parameter, second object in the array will be I first level B, the actual implementation, the actual instance concrete type, which is first level B. So the end result, after we're all said and done, the constructor parameter will have those instance types created. So I need to loop through all the constructor parameters that exist in the constructor. So for var I equals 0, Telsense help me out there. So I created the loop to loop through all the constructor parameters. In this case, it's going to be 2 in this first iteration for root class. And what I now need to do is I'll get the constructor parameter for the current index that I'm at for this first one. Constructor parameter equals constructor dot get parameters I. So this will get, for this first pass through in the loop, the index will be 0, the first element in the constructor parameters, and for this will be the I first level A. So it'll be the parameter of I first level A that I'm dealing with here for this first pass through in this loop. So that's what's represented in this constructor parameter. This constructor parameter is a parameter info, though it's not the type. So what I need to do now is get the type that it is. So call constructor parameter type equals constructor parameter dot parameter type. So now this is the actual type that I can use to look up the next mapping. So this is now I first level A. So going back to here, I first level A mapped to first level A, and if I go down to here, first level A was right here, and first level A, that actually has parameters too. It has constructor parameters as well. So I need to construct those things before I can actually create a first level A. So that's where the recursion is coming in. So jumping back to here, and now the parameter type, and what I need to do is actually create this instance. So constructor parameters I is going to be get object. So I'm using this generic thing. Generics require the strongly typed generic to be used, so like I root class, but right now I'm using reflection, so I don't know the type at compile time, which is what generics grants you. At runtime, I'll have the type. So I can't use this method anymore. But what I can do is create like a pass-through. So let me create something that will do the exact same thing, but just get rid of the generic and just deal with types. So get object. We'll make this private for the time being. The only thing that can access this is the IoC container itself. It's debatable whether we should expose this to everything, but let's just ignore that for now. So we want the type, and this is the from type. So this is from type iRoot class, and we're going to get an instance of a root class as the to type. But there's no variable name for that. But I'm keeping this from type because this is what we're trying to create from. So I can pretty much just copy this directly, and I'll show how I can change up there. I just need to get rid of these type ofs, because now I'm not dealing with generics. I'm dealing directly with the type. So I can just put from type where I see type of t. So let's do that here. Let's do that here. And I can delete this now and just do return, get object, and type of t. Oh, and I should cast this as t. So now if I'm using this generic representation, I can now comfortably, instead of dealing with an object where I don't know kind of like what exactly it is, I can cast the object to be the generic type that I used in this method and it'll return it. So for example, it'll be an iRoot class. So here, this will return a root class at the end result, but it'll be of type object. So the caller of get object won't know what to do with it. It'll be difficult to use. Adding this cast right here to return it as the iRoot class makes it a lot more flexible, and the caller will, since it already knew it needed an iRoot class, can treat the result as an iRoot class. So going back to here, I couldn't call this because I don't know the generic type that it is, but I do now have the type right here, the constructor parameter type. So I can recursively call get object with the constructor parameter type. And that's our recursion right there. So for this first iteration, iRoot class comes in as the type. It'll find root class. Root class has the I first level A, I first level B as the parameters in it. So this parameter type for this first iteration in the loop is I first level A. So it'll pass I first level A up to here. So the type right now is I first level A after we've gone through the iRoot class for the first time. So I first level A here, it'll find first level A in the mappings, go through here. There'll be two parameters in it, I second level A and I second level B, and it'll have to do the same thing. So this will call with I second level A as a constructor parameter. It'll come into here, find a mapping, I second level A goes to second level A right here, and the to type is second level A. And if you remember, second level A doesn't have a constructor. Well, there's a default parameterless constructor implied. That's always there. So there's no recursion for this because there's no dependencies that I have to look up to recursively create. So I can now actually create the second level A for this. So for second level A, this will in essence be bypassed because there are no constructor parameters. So I can just return an instance of second level A. So typically how I do that is just return new second level A. Unfortunately, I can't do this because I'm dealing with reflection. I don't know the type at compile time. I only know it at runtime. So the only way to create instances at runtime, or one way to create instances at runtime, is to use the reflection method activator, create instance. And this will be like the same as this. The end result's the same, but instead of creating it using the strongly typed language, the safety of that, I'm now using the reflection counterpart to it, which I kind of lose the strongly typed benefits. But that's fine because that's what the purpose of this exercise is. So activator, I create instance, and I have the to type. So again, this is the concrete type that I'm trying to create, and I need to pass in the constructor parameters. So this, at least for the example, if it's a I second level A passed into here, this will be bypassed. Second level A is returned here. This is the strongly typed representation again. I don't know at compile time what type it is, so I have to use this reflection method to create the instance of the types. So that way, remove that, and yeah, this should in theory be all we need, and this should work. So let's go into here, and yeah, I should be able to uncomment this and set this to a variable. So var root class IoC equals, okay, that's good, it's not red, so looks like that's working. And let's just let's output this thing. So called it root class IoC and console.writeLine, and I don't want anything in there, just a spacer. And yeah, if we did this correctly, this hopefully works. So let's run it. So running it, yeah, it looks like it worked. Again, this first root class is the Pure Dependency Injection implementation I did up here, right here, and the second one is our IoC Container representation, which is right here. And both have unique GUIDs, and that all looks good. So I think we did this right. I just want to go back to kind of the problem I was talking about with constructors, having multiple constructors. So let's go into here and let me add an additional constructor, public constructor to this. So root class. So now there's a public constructor, and in essence there's now two public constructors. And the problem that we're going to run into is that the dependency injection container will not know which constructor to actually use. So if I run this, I get this exception, sequence contains more than one element, because I added that. I'm expecting only a single constructor to be in the list of publicly available constructors for that type. In this case, root class doesn't have that, so that's why that failed. And I think that's pretty much it. Let's just get back into our working state. So go into here, let's remove this. And let's run this again just to make sure we didn't break anything. And yep, it all still looks good. So yeah, let's move on to the next section. Welcome back to normal speed. Actually, I'm just joking. I wasn't talking that slow at the start. I just wanted to see what would happen. Anyway, what I went over this previous coding example was known as a transient scoped setting. This is where a new instance is created every single time within the object graph, even if the same interface or abstraction is utilized in the object graph. So the I second level A, I second level B, even though they were the same type reused across I first level A and I first level B, they were dependent and completely new instances of those objects in the object graph that's generated in the root class. For this next thing, I'm going to go over something called a scoped lifetime setting. So like I was saying, these are transient states. If I run the application again, you'll notice that the GUIDs are all different. So this second level A right here is a different GUID than this one here, which means the second level A in first level A and the second level A in first level B are different instances of those objects. So you might run into a situation where you want to have the same reference for both. So as you can see right now, this new right here creates a new second level A, this one creates a new second level A. So what would happen if I wanted to do one that utilizes the same reference of second level A and second level B? So to do that, I will create a var second level A equals new second level A, and var second level B equals new second level B. And let's create a new root class, a scoped one, equals, I'll just steal from up here, paste that, and instead of inlining a new second level A and new second level B, I'll use the second level A that I created up there and the second level B right here. And same thing for this, I'll use the same second level A and second level B. So now first level A and first level B are using the same second level A and second level B instance objects. So to run this, let me just add some additional stuff here. So these are for transient. And let's do a spacer. We'll just write an empty line. Put some visual indicators to there's a separation. And let's do console.writeLine scoped. And let's write the object graph for our newly root class scoped instance we just created. So if we run this, we now see that second level A is EC8 and for first level B, and second level A for first level A is the exact same value. Similar for second level B between first level A and first level B. They're both the same instance of that object. So this is a scoped lifetime setting. So to incorporate something like that in our IoC container, let's jump back into here and I'll add some additional concepts. So public enum, this is just going to be a list of all the different lifetime settings there are. So right now we have the transient one. And now we're adding a new one called scoped. Again, scoped is just when the object is when the object graph is getting created, it will reuse the same scoped objects that are bound to the scoped lifetime setting. And I'll also add an additional class that will utilize this lifetime setting. So before, I had mappings going from a type to another type. I'm not going to have the type be the key, but the value will now be a type with lifetime setting. There's going to be a wrapper of the type with lifetime setting enum that I just created. So let's create that class, public class type with lifetime setting. And for this, there's going to be a private type private lifetime setting, and actually let me make these private because nothing needs to know about these internal concepts. We'll expose kind of these concepts unbeknownst to the user, but behind the scenes, this stuff will be being utilized. So they're private, they're only accessible within the context of this class. Nothing external knows about these concepts. This type with lifetime setting and lifetime setting. So let's create a constructor for this type with lifetime setting, and that'll take in a type and a lifetime setting, and it'll just set those values. Yep, there we go. Proper spacing, formatting, and let's just expose it as getters. So public lifetime setting, and I'm just going to return lifetime setting. And similarly for type, public type, and that just returns the type. So again, new lifetime settings, transient, we've already done. Adding the new concept of scoped, adding this new wrapper which has the type and lifetime setting, and let's put that up here. So instead of this being a dictionary of type, it'll be a dictionary of type lifetime setting, and this will come up incorrectly. So let's do type with lifetime setting here as well. So right now we have bind by default it's doing transient. We should probably be a bit more explicit. So within here, we're binding. This is transient. Let's rename this function to bind transient. This will apply across everything. So rename to bind transient. You can see bind transient has been renamed here because we're setting up transient bindings. And let me add a private void bind that will now have a generic from and to what it's mapping from and going to, and it'll pass in the lifetime setting. And with that, we can create the lifetime setting instance by picking the type of 2 and passing in the lifetime setting. Let's see, I seem to have messed something up. This first takes in the type. Not containing a constructor that takes 2 arguments. Oh, this should be type with lifetime setting. There we go. And what's going on here? Lifetime setting. Cannot use. Oh, I'm using the same name, so let me call this type with lifetime setting. There we go. And IntelliSense knows what I'm doing, so I'm mapping the from to this new type with lifetime setting. Again, it's just the same thing. It has the type that I'm mapping to, but just with the lifetime setting for the lifetime of the object for the dependency injection container creation of an object graph. So let's change this now to now call bind, and this will be the from to, and we're just going to pass in lifetime setting transient, and that should be good for that one. Now we're going to add additional binding availability. This will be the scope one, so bind scoped, and this will be scoped here instead of transient because we're binding scoped. So now we have the mapping set up appropriately, and we now need to update the object creation. So down here, you can see same things. Just want to still ensure that the key exists. The from key from the mapping is still the same. So this line doesn't need to change. But when we get to here, this changes a little bit. So it's not the type now. It's not the to type. This is actually the let's create a new variable var type with lifetime setting, and that's just going to be this right here. Because again, remember, this is now the value of looking at this key is the type with the lifetime setting in it. So the to type is just going to be type with lifetime setting dot type. So now this should work the same, and this doesn't need to change. This doesn't need to change. This doesn't need to change. What does need to change though is when we get down to here and actually let's go up here. So this get object, this is the recursive thing. So scoped is going to have kind of like a list of instances that have been created during the object graph creation. So right now I'm not referencing anything that is scoped. I'm just still in the transient mindset. So probably this should change to be taking in a dictionary of type, and this type is going to be the from type again. And what it's going to is an actual instance object that's created from this line. We'll have to keep adding additional mappings, I won't call it mappings, adding additional key value pairs to this dictionary for instances that have been created through this process to continually reuse them if one is created and the corresponding mapping is of the scoped lifetime. So instead of this being of type, this will be a type object because we've actually created the object down in here. So we'll call this the scoped instances. And I'm going to do one more thing. I'm going to add an additional get object. I'm going to overload the method name. I'm going to reuse the old one that we were using. The reason for that is I'm just going to, this is a pass-through thing, just to kind of initialize this this new parameter in get object. So I don't have to keep handling, like, creating this scoped instances and like passing around. And yeah, you'll see what I'm talking about in a second. So I'm going to return get object. So we have the from type, and we're just going to create a new dictionary of type object because that gets passed down. So now how this will flow is when get object is called, this will call down here. This get object will then call this one, but it will initiate the scoped instances in an empty dictionary. So as we're going through, it will append to these scoped instances, and recursively, we'll have to now call this one to keep track of the scoped instances for future access and use to rely on. So let's go back down to here. So instead of calling get object here, I'm going to call the new get object with the scoped instances. So now recursively, we'll call this one and retain the scoped instances that have been added. As of right now, I'm not adding any scoped instances. That's going to have to be done down here. So instead of just returning this, I'm going to set this in variable var instance equals. So now we have an instance created, and I need to now check to see if I need to keep reference of this instance to potentially be used again somewhere else in the object graph because it's a scoped lifetime. This instance should be a scoped lifetime for the from type that's being utilized. In this case, it's going to be the I second level A and I second level B. So if we do that, we will check to see if the type with lifetime settings dot lifetime setting is equal to lifetime setting scoped. And if it is lifetime setting scoped, we'll add to the scoped instances. So this should be from type, and this should be the instance. And again, if this is just transient, it'll bypass this and just return the instance itself. It's not appending to the scoped instances because it's transient. It's going to be created. A new one's going to be created every single time. So now the last piece we need to do is when we're getting a parameter type, again right here, we have to create an instance of the constructor parameters. So like in here, we're trying to get an iRoot class. iRoot class binds to the root class concrete type, and the constructor for root class has these two dependencies. These two dependencies need to be created before the root class can actually be created. So within here, that's what that's doing. That's what the constructor parameters are being set to. In this one, it's being created through this method. Like it has to go through the more like kind of like the transient type of process. But if it's scoped, this can change a little bit. So what we can do is if scoped instances that contains that constructor parameter type, we can now use the scoped instances to get the instance type that is represented. Because if this type is represented, this from type is represented in the scoped instances, it's guaranteed to be at the lifetime setting of being scoped. So let's do that. So constructor parameters I, Constance was smart with this one. So instead of recursively calling to get the object, it actually has it right here as one of the key value pairs, and that's what's being set right here. Else we default to our old way of doing things and get the constructor parameter, that index, to be set by recursively calling this. So this in theory, hopefully, will be what we need to see this work. So let's create a new container. Let's see, this is, let me move this up here because that should be closer to what's actually using this. This root class IoC was using this container. And let's call this container transient. It's a transient container that covers the best of our transient use case. So let's now do a var container. Instead of calling it scoped, no, call scoped. Var container scoped equals a new IoC container. And we pretty much just steal what I did up here. Let's do that. And instead of these last two being transient, let's now make them scoped. So again, the scoped means that the second level A and second level B are going to be using the same instance types wherever we see the I second level A and I second level B. So it's going to be how this pure dependency injection is utilizing them. So let's create the var root class IoC scoped, and that equals the container scoped dot get object, and this will be my root class because I want to get the root class for printing the object graph as a string. And let's steal this, paste that, and instead of this being root class scoped, this is root class IoC scoped. And let's run this, see if we have any errors. Yep, we have an error. We did the same mapping twice in our bindings. Let's take a look at where we messed up there. So in here, we bound to iRoot class A. Now let me run that again. I think I missed what actually. I figured I'd duplicate the same thing twice. Imagine with the same key has already been added, key console app.iRoot class. So looks like somewhere I'm adding the iRoot class twice. Let me see if I can find where that's happening. So under program, container scoped. Oh, should be, no, that's right. Container scoped. So I add the iRoot class. I'll just put breakpoints. I'm not quite sure where this is breaking. So this somehow already has that mapping in there. Already has 5. Where is this happening? Oh, I copied the container transient. So I'm using the container transient. I'm not using the newly created container scoped. So let me update that. I mean, this is development. So let's try this again, and hopefully we don't run into issues now. So ran that. Oh, so it successfully ran. And let's see how we did. So first level A. So this is these are the scoped ones. This is the pure DI, and this is the scoped for the inversion of control container. And first level A, this has second level A as this value 5FC3. And if we look at the first level B with the second level A, this is also using the same one 5FC3. And likewise, second level B for the first level A has A0, A7. Same thing with the second level B. So that looks right. And yeah, let's let me just do a quick modification just to make sure like I've got this right. So let's say we want to use the same instance of I second level B every single time across I first level A and first level B, but I want to use different instances of second level A. So instead of doing bind scope, let's do bind transient. Let's run this. And what we should get is A should be different between the two. So this is BFDC, and this one is 45B5. So that's what we were expecting. They're different, so that's good. Second level A is different between the two instances of first level A and first level B. And second level B, since that's scoped, has the same value, is the same instance across both first level A and first level B, which is what we're expecting. So in this scenario, this passage looks like this is working correctly. All right, last but not least is the singleton. The way this is supposed to work is that across these get objects of the container, the instances should be the same. So for example, I mean, like doing Pure Dependency Injection, doing something like this. So var, let's do second level A, singleton equals new second level A, and root class first. And this will use second level A singleton. And subsequent call, oop, that looks weird. Let me try that again. There we go. Subsequent call will have the same second level A singleton. This is the pure DI approach. It's not like really one-to-one with what we're doing here because this is not technically a singleton for the whole application. The singleton's for the whole application. So in essence, this is what I'm going to be trying to do for adding a singleton lifetime scope for this last part. So in order to do that, we'll jump back to here, and well, we have the bind transient, we have the bind scoped. We know we're going to have to add an additional one, which is singleton. So let's go back up here and add that method. So I'll just copy this bind scoped one. It's going to be pretty much the same. So instead of being bind scope, we'll call it bind singleton, and the lifetime setting is going to be singleton. So now we can bind a singleton, which is cool. And the next thing we want to do is pretty much just append what's currently here. So for the scoped, we had kind of a short-lived scoped instances that exist only in the context of the get object. That worked well for scoped, but this is a singleton, so we need it represented for the whole context of the container. So instead of being a parameter within a short-lived instance within a function of the parameter, I'm going to pull that concept out into here at the top level. So we'll keep an instance of singleton instances that exist in the container. So I want to be clear, I'm not dealing with concurrency issues. We can address that later. Again, this is a simple example. We'll assume this is single-threaded. It's not thread safe because it doesn't prevent multiple things from adding a singleton. So we can not worry about that for this example. So dictionary type, and again, it's going to be an object with the scoped instances, but now these are going to be singleton instances. Again, I'm moving it up here because this has to be existing across multiple calls. The only way to do that is to have this instance variable be accessible from getting objects multiple times through the container. So we'll just set the singleton instances this way and tell us to pick that up. That's awesome. And yeah, it's pretty much just going to be adding additional checks and scenarios for here. So we check to see if the scope instances contains the constructor parameter type. Again, the way these mappings work is all the types are going to be unique, so you can't have like I second level A represented twice. So since I second level A or any other type can only be represented once, you can't have multiple lifetime settings for a specific type. So that's why we can just run down the list of if it exists in scoped instances, then that binding only exists for scoped if it finds one. Otherwise, it only exists for transient, and I'll add the additional one for singleton. So the singleton instances that contains the key of the constructor parameter type. Then same thing here, we'll just steal this, and instead of this being scoped, this will be singleton instances, and now we get the singleton instances. And likewise down here, same sort of concept. Instead of adding it to the list of scoped instances, we're going to add it to the singleton instances. So now that's added, and that should be pretty much all we need for singleton from an implementation standpoint. Let's see if we actually got it to work. Again, since we built up a lot of the foundation, adding the singleton was relatively straightforward. So let's create a new container var. I'll just steal this and rename it. I'll be sure to rename it and not make the mistake like I did last time and use the same thing. So this will be container singleton. So I'll use singletons. And for this one, I'll use the bind scoped here. So the second level A within the object graph of just getting one instance of iRoot class will have the same second level A instance represented within that one object graph. On a subsequent call, it will be a different one. You'll see when we write to output. And the bind singleton will be the same instance across multiple calls to getting the iRoot class. So second level B will be the same across, in this case we'll do two, but multiple getting the instances of iRoot class. So let's do a var root class with singleton first call, and we'll do container singleton dot get object, and we're getting the iRoot class. And we'll just do another one. This will be a second call, and we'll get the iRoot class. So, for example, the root class with singleton first call will have I second level A will be the same instance within the object graph of this. And then within the second call, it'll be a different instance of I second level A between the first and second call, but within the actual object graph, the second level A will be the same instance. With singleton, the second level B across both calls will be the same. So both root classes will have the same instance of I second level B represented in it. That's in theory if we did this right. So let's add one more separator. So this is going to be singleton, and we're going to print out the first call and the second call. So we run that. Hopefully we don't have any errors. Don't see any errors. So here it is. So let's take a look at the scope. The scope is still working. So there's that and that. So second level A and second level A are the same, and they're different across the first and second call, which was expected because second level A was a scoped lifetime.
Now second level B should be the same across both calls. So here we have this, and within the same object graph is the same, so it's the same as the second level B within the first call, and we're looking for 3622. And as you can see, in the second subsequent call, it's the same as this 3622. So the singleton is actually working as expected. And there you have it. That's the implementation of kind of a rudimentary, but functional inversion of control container or dependency injection container.
What I've come to realize is an interesting design principle comes out of working with dependency injection containers in your code. There's almost a fear of creating inline objects throughout the application flow of your code base. The word new is almost entirely non-existent outside of the inversion of control container code itself. So therefore, I've coined this term the inversion of newing design pattern. At surface level, this kind of implementation seems very good. I mean, you're not relying on specific implementations within your application code. It's the purest dream of loosely coupled code. But just like there's an issue with too tightly coupled of code, the pendulum can swing the complete other way, and there may be issues with too loosely coupled of code. The downside of tightly coupled code is that when a requirement comes in to change the functionality of the code, parts of the application may change that shouldn't be required to change. The canvas class is a good illustration of this. The canvas class just needs to draw anything. It doesn't care what, just that it can draw. So when the requirement came in that changed what the canvas was drawing from a rectangle to a circle, I had to explicitly update the canvas class to use a circle. This is one of the downsides of tightly coupled code. On the other hand, if the requirement was still to draw a rectangle, but current output was actually drawing a triangle, I would still need to make code changes, but these code changes would be in the proper and correct location, the actual rectangle class. I would need to go in the rectangle class and actually make the change to draw a rectangle instead of drawing that triangle incorrectly. The tightly coupled problem still exists in this code base, but it's a moot point here. This example demonstrated the good parts of tightly coupled code. It grants the developer readability and understandability of how the system will behave when a coding change is made. When I made the change to the canvas class to draw a circle instead of a rectangle, that was easily understood as to what was being changed and how it would behave. When I was trying to draw a rectangle and was actually drawing a triangle, I knew exactly what was wrong with the system. Too loosely coupled of code has the advantage of making changes to the code for requirements in the proper location, but at the downside of losing understandability of how the system behaves when that change is done. Let's revisit the eye shape again, and assume we want to have characteristics as to how to draw the shape, maybe like size or color. So for this, we'll add an additional argument to the draw method that takes in a generic object, because we don't want to be tightly coupled to the attributes that the shape should be drawn in. Now let's assume that we want the rectangle to be green when we color it in. So let's add to the object that the property color is green. Now let me stop there and ask you, what's the result of this? The answer is you can't know what it is. You can't look at the code and figure out what's going to be drawn here. Is the rectangle actually going to be colored in green, which is what I want? Maybe the outline is going to be green. There's always the possibility that nothing happens at all. In order for me to know what's actually happening, I probably have to run the whole application in integration, or have to go to the specific eye shape that is being utilized in the canvas to know what's going on, and that's not an easy task. Again, the main drawback here is that the reader of this code will have no idea how this is supposed to function in this extreme illustration of loosely coupled code. You will have to run the whole application in integration to know what is actually happening. Or you have to read the code very specifically to know what eye shape is actually used. This is the downside of loosely coupled code, a loss of readability and understandability of that code. So the simplest of code changes in one class could have the most complicated comprehension of how that affects a system as a whole. Revisiting my previous video on interfaces again, loosely coupled code has the issue of prematurely creating abstractions that don't actually work. Now, when I say premature, I mean incorrect abstractions that shouldn't be used. It's ironic because you thinking you're creating loosely coupled code with these premature abstractions later on could tightly couple your code to using these incorrect abstractions. Like how I mentioned that the canvas class, depending on the iShape explicit interface, may not have been the best explicit interface to depend on. What if, for example, I wanted to draw a line, or multiple shapes, or a tiger? Or maybe I'm just drawing this video right now. Whoa. I wouldn't consider a tiger to be a shape, nor would I consider drawing this video to be a shape. I'd probably more consider it to be an iDrawable, for example. So not only would I need to update the canvas class to rely on the iDrawable interface now instead of the iShape, I would need to update all the implementations that are explicitly implementing the interface iShape to use iDrawable. Then the next question becomes, is the iShape explicit interface even useful in my code base, because I'm probably not relying or utilizing it anymore. So what was once thought and intended to be loosely coupled code is now actually a tightly coupled concept within my code base. I'm sorry, I lied. I'm going to pull out the prospect processor again, but it's not going to be the same as last video. I'm going to show you the construction of the object graph of this thing. As you can see, it's 16 dependencies wide, but it's also 10 dependencies deep. I've never in my experience seen something like this that existed outside of an inversion of control container. So you can see I'm doing the poor man's dependency injection here, and this is why I favor this exercise. It kind of shows how difficult and wonky, I guess, this thing actually is when you do it at full construction. I think seeing this and realizing this, you might think that there is a red flag and something is amiss here. Finally, please don't get fooled. You're coding still to these explicit dependencies, these concrete classes. Inversion of control is just hiding this fact from you. The specific class that is loosely coupled to a concrete class from the dependency injection is still underneath it all, still relying on that explicit concrete type. To be clear, I'm not advocating for you not to use dependency injection containers. This is quite a beneficial design pattern to use in your codebase. It is an exception to the rule for the majority of your codebase, though. This is not the rule for the majority of your codebase to follow. Looking at the canvas class again, and its dependency on iShape, I'm wondering if the rectangle is the only thing that ever should be drawn in the canvas. Is the general use dependency management system the proper place to invert control as to what should be drawn in the canvas? For example, I would imagine maybe a state change occurs or some user interaction occurs that allows the canvas to now draw a circle or a triangle. How would you even code for something like this in, like I said, a general use dependency management system? Maybe logic that sets dependencies, especially dependencies that are domain specific, don't belong at this level of abstraction, this inversion of control container. The question I guess then becomes, where do they belong? Well, anyway, thanks again for listening. This is just, again, another one of my strongly held opinions, weakly held, of course. So please leave a comment in the section